Hello, and welcome to Computational BME. In today's presentation, we'll be talking about computational thinking. As an application of computational thinking, we'll be thinking or looking at robotic hands, and they provide a nice challenge in computing that's relevant to biomedicine because our own hands are highly nimble or dexterous, and it can be very challenging to program a computer to do tasks that our own hands can do. And one of the areas of competition in robotics has been in designing computer-enabled hands that can, in this case, solve the Rubik's Cube just with one hand, even with additional challenges such as including a rubber glove or pushing on the cube with a plush soft toy. I encourage you to watch videos of this in action at the link below. So as the application for our problem set 1, we'll be thinking about similar situations of a robotic arm or a prosthetic that replaces the natural arm. And I'd like you to imagine that you are an engineer and that you're designing a controller for this robotic hand. And there are only a few things that you can control. First, you can rotate the wrist 1 degree clockwise, or CW, or 1 degree counterclockwise, or CCW. Or you can open the fingers by 1 motor step. Or as a fourth action, you could close the fingers by 1 motor step. So those are the things that you can control. And the things that you can receive or inputs from the sensors would be the neural activity. That would be the neural activity coming from the arm that might be wired to this robotic arm. And we're going to assume that that's a value between 0 and 1, for 0 as in no signal and 1 as high as it can go. We're going to assume that you can also receive inputs from force sensors that are in the fingertips. So that would be the finger force. And finally, we're going to assume that you can measure the wrist angle so that you know when you're rotating that angle how far you've rotated. And so with using this combination of actions and sensors, you're going to be writing out programs to look at how to control the robotic hand. And so in the process, you'll need to apply the concept of computational thinking. So what do we mean by computational thinking? Well, it involves a few steps. First, it's really important to clearly state your objective. Next, you're going to develop an explicit step-by-step procedure or algorithm for achieving your objective. You're going to implement the logic of this algorithm using control structures. And so some of the common control structures you'll encounter are if-then-else statements, loops that are while loops or for loops, and also considering inputs and outputs for your programs. It's really important that you can measure when you've achieved your objective so that the computer knows when it ends. And finally, you're going to want to incorporate error handling, debugging, and validation tests. We'll look past these for today's application, but as you start to write your own programs, these will be incredibly important. And finally, we're going to be using flowcharts, especially today, and later pseudocode that helps you develop and demonstrate computational thinking. And one of the things that I really like about flowcharts and pseudocode is that it abstracts or simplifies down the thinking process when it's not even just in the specifics of an individual language. Once you start coding it, it gets complicated about syntax errors and things. But if you look at the flowcharts or pseudocode, you really get to the core of the computational thinking for that problem. So how do we make these flowcharts? Well, here are a few standard symbols that are often used in flowcharts. We have this pill shape that indicates the start or end of the program, flow lines that show direction of logic flow, that connect the different symbols. We have this trapezoid that denotes input or output operation. We have rectangles that denote a process being performed. And finally, we have these diamonds that denote a decision or branch in the program, such as an if, then, or else statement. Okay, so let's look at our first flowchart. We've got this cute little guy here, and he's deciding to eat, right? And so we can start up here at the top, and it says, am I hungry? And if the answer is no, well, then he can go and play. However, if he is hungry, then he should eat. And then that would go to the end. So that's an if, then, else statement. Our next example of a control structure would be if you're having him open and close his mouth 5 times and then swallow. One way you could do this is to say start, put food in mouth, open mouth, close 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 mouth, and then swallow. But that's really redundant and provides a lot of opportunity to get things wrong. So instead, as an alternative, we can use a loop that would allow us to condense the logic of what's going on. And so we can replace these many different steps with a for loop in this case. The reason why we'd use a for loop is because we already know how many times we want to repeat this. And so if you look on the right, open mouth, close mouth, and then you just repeat that for up to 5 times, and then you swallow, and then it's done. This simplifies the computational thinking, and it also reduces the amount of errors that you might have by accidentally coding in problems with such a long code as on the left. The next type of control structure we would like to think about is a while loop. And so a while loop is used when you don't know how many times you want to run something, but instead you want some sort of sensor or detection that tells you when you're done. And so in this case, if we want to chew as many times as possible until it's all chewed, we could have this decision. You put food into the mouth, then you ask, is the food all chewed? And if not, you're going to open mouth, close mouth, and repeat. Once the food is all chewed, then we're done. We're going to swallow, and that's the end. One more thing I'd like to point out is that you often see that in these examples, as they become more realistic and complicated, that we're going to be needing to use the counters, the loop counters, in the computations themselves. And one kind of cute example of that is in the song The 12 Days of Christmas, which you likely are aware of whether or not you celebrate Christmas. And the basic idea here is that there's a building structure of components where on the first day of Christmas, my true love gives to me a partridge and a pear tree. The next time is 2 turtle doves and a partridge and a pear tree, and it repeats in that way. And because there's a repetition, that gives you the hint that you're likely going to need a loop structure. And so on the right-hand side is at least one version of a computational thinking implementation with a flowchart, where if we would have a counter for which day before Christmas it is, and that we're saying, on the 9th day of Christmas, my true love gave to me. And then you're going to sing lines I through 1. So the first time is just going to be a partridge in a pear tree. And then you're going to repeat, add, do the next day. And so on, and then you'll be done. So one thing you can see here is a somewhat complicated song can be simplified down into a rather compact flowchart. So now, considering these different steps of problem solving using flowcharts and control structures, let's go back now to the problem set. So in the problem set, you're going to be asked to program a robotic hand to rotate in response to neural activity. So this neural activity is going to be between 0 and 1, and you're going to calculate the change in wrist angle, and then you're going to have it rotate the appropriate number of degrees. This isn't enough detail to show the computational thinking. We want you to put in more detail about how you would actually do that using only the actions that you are directly given from the start. You can't move more than 1 degree at a time. And so you need to keep these constraints in mind. And then what you're going to be doing is to draw a flowchart of this process adding step-by-step detail that replaces what you see here in these bolded boxes. The next part of your problem set, you're going to do a different challenge, is you're going to be looking at how you would program this robotic hand to grab an egg without breaking it. And the basic idea is that we're going to imagine there are force sensors within the fingertips there, and that the robot is going to keep closing its fingers until the finger force exceeds some threshold force that would be about the force that causes to break the egg. And so a couple things to keep in mind is, first, this is where it keeps getting the finger force. It's going to be continually updated with the current finger force, and that is happening until you reach this threshold. And so you're going to code in or add to your flowchart the things that would replace what's in this bolded box right here. You're going to draw a detailed flowchart for this process. So in summary for today, we've talked about how computational thinking is critical for solving complex problems. It involves clarifying the objective, breaking the problem into chunks, and defining the logical decision-making needed to accomplish the objective. Flowcharts and pseudocode help you demonstrate computational thinking before you actually get to the computer to code it up. For and while loops, if-then-else structures are key control features of computational thinking that underlie most of the decision-making problems you'll see in the rest of this course. Some of the tasks you'll get are more complicated, but they can be broken down into these simpler components. So thanks, hope you had fun, and I'll see you next time.